So today we will be finding the horizontal force that water exerts on a dam. So here is our water. It is a height of lowercase h, and our dam has a height of capital H. Our dam has a trapezoidal shape with a top width of T and a bottom width of B. And again, here is that horizontal height, capital H. So because our liquid exerts a pressure on our wall over this cross-sectional area, there will be a force due to pressure. So we know pressure applied at some cross-sectional area will result in this force, and so force is equal to pressure times area. We also know that pressure changes with height. So we're going to start with dP dz is equal to negative rho times acceleration due to gravity to find what our pressure is. To get to this equation, it was explained in a previous video. So first we are going to start by simplifying this to say dP, so our change in pressure, is equal to the negative density times acceleration due to gravity multiplied by the change in height. And we'll integrate both sides, and our pressure one will be from pressure 1 to pressure 2 to a location Z1, Z2. We're going to define the upward direction as Z, and this way will be positive X. When we integrate this, we get P2 minus P1 is equal to the negative density times acceleration due to gravity times the quantity of Z2 minus Z1, where this location is Z1, this location is Z2, there's some pressure here, and the pressure here we're going to say is equal to 0. Since we define this as our upwards direction, we're going to say that Z1 is equal to 0 and Z2 is equal to lowercase h, which is the height of our water. Plugging these in, we get that the pressure is going to be equal to negative rho gz. So now back to force is equal to pressure times area. We have the force is equal to, now our pressure is going to be P ATM minus rho g z times our area, where since we are working in gauge pressure, our PATM is going to be equal to 0. So we get negative density times acceleration due to gravity times the height times area. Since pressure changes with height, what we're going to do is cut this trapezoidal area into tiny cross sections where over that tiny area, the pressure is the same. So our area will be changing. So the negative density times acceleration due to gravity times z, or height, times the change in area, which can also be written as negative density times acceleration due to gravity z times x dz, where x is our width and z is the height of our area. So to do that, we are going to say that here, halfway between our width of t and halfway between our width of b will be 0, 0. And this point here is going to be the width of b divided by 2, 0. And this will be the width of t divided by 2, because it's halfway between, from here to here, it's half the top width, comma, h, because our height of our trapezoidal shape is capital H. So our equation for this line, the slope is going to be the top width minus the bottom width over the height, and that's going to be multiplied by 2. Because our shape is a trapezoid, our width is going to change with our height. So we need to find a way to express our width in terms of z, our height, to put into this equation. and that will be our slope. We're gonna write this so that it's easier as capital M throughout the remainder of the problem until the very last step, instead of writing this entire portion. So then what we get for the equation of the line is going to be x, which is our width, is equal to capital M, this part here, times the height, plus the bottom width here divided by 2. To find this equation, we used this point here. So now we can plug in this expression to here for our width. And what we'll get is that it will be equal to the negative density times acceleration due to gravity times z times capital N z plus our bottom width over 2 dz. Because of how we defined our points here, we'll need to multiply this entire part by 2, which will now be equal to our change in force. So we want to go ahead and integrate both of those sides. We're going to integrate the force from the force at height 0 is equal to 0, because when there is no height, there will not be any forces yet, because we have not totaled anything up, all the way to our final total force. And then for this integral, it'll be from z is equal to 0 to z is equal to lowercase h, which is the height of our water. So to simplify this a little bit, we can pull the density, acceleration due to gravity, and 2 out of our integral. And we will get the change, the integral of our force is equal to f0 all the way to from 0 to our total force is equal to negative 2, the 2 because with how we assigned our points, if we don't multiply it by 2, our integral will only be half of the trapezoid shape, times density times acceleration due to gravity. The integral from z is equal to 0 to z is equal to the height of our water. We can distribute this z out, so what we get is mz squared plus bz over 2 dz. So when we integrate that, we get that our total force will be equal to negative 2 times the density times acceleration due to gravity times the quantity m, h, little h, which is the height of our water, cubed over 3, plus the bottom width times the height of our water squared over 4. We aren't done yet because we still need to substitute this expression back in for m. So what we get is that our total force will be equal to negative 2 rho, which is density times acceleration due to gravity, times t, which is our top width of our trapezoid, minus b, the bottom width of our trapezoid, times the height of our water cubed over 6 times the height of our trapezoid, or the height of our dam, plus the bottom width of our trapezoid times the height of our water squared over 4. And that is the total forces in the horizontal direction that the water exerts on our dam.